So the more you can keep the organic carbon into society, the better. And if at the end you still need to get rid of the organic carbon, you can still burn it and harvest the energy. The energy is not gone if you recover it as a material. If you recover it as energy, the material is gone. And in the Netherlands, we are looking to and have been involved in 3 recovery options, which are now all 3 quite close to practice, at the brink of becoming fully commercial. They're not 100% commercial, but they are not far away anymore, showing that wastewater treatment plants can become energy efficient. Now, if you would do resource recovery, it's often said as that resource recovery, organic carbon recovery, is competing with energy production. Well, that's not the case. We are not there yet that we can convert all the organic carbon into valuable resources. Unfortunately, until now, it's effectively a relatively small amount. On the left-hand bar, sorry for the Dutch on the graph, that's how the current situation is. Blue is the amount of organic carbon in the influent, which ends up in the effluent. Green is the organic carbon in the influent ending up in the sludge. And gray is the organic carbon in the influent, which is oxidized into CO2. Now, if you implement cellulose recovery and recovery of EPS, the picture changes a bit, but there's still a significant green area for energy production. So there is an impact, but it's not completely that one excludes the other. It will be somehow going together, integrated. And maybe one might benefit from the other. I will come back to that in a minute. I just want to introduce you these resource recovery, because I think from a carbon neutrality point of view, these options are way better than, for instance, going to anaerobic digestion. Cellulose, if you throw toilet paper in the toilet and you flush it away, in the Netherlands, roughly this is 10 kilograms per person per year on cellulose, which can be recovered. So that's a huge amount. I have no idea on toilet paper consumption in China. I know in the US it's 1.5 to 2 times more than in the Netherlands. You can very efficiently get it out with a simple fine screen, a sieve, sorry, not a screen, a sieve. The technology is there. It can be recovered. On these plants in the Netherlands, these which are indicated on the country map, the cellulose is recovered. Advantage, at 10 degrees Celsius, in the winter temperature in the Netherlands, cellulose is not degraded, just ends up in the sludge, and it contributes to the sludge production. So you minimize sludge production, certainly in the winter, and a bit less in summer. At 30 degrees, cellulose is usually completely degraded. So it depends, very temperature dependent how efficient it is. But it's a lot less sludge production, which easily pays for the cost of sieving out the cellulose. There's a company called Recell now in the Netherlands. They collect this cellulose and they develop a market for the recovered cellulose. Now, one of the aspects we have been looking at is converting that cellulose into nanocellulose, because if you want to produce nanocellulose, you first have to delignify the cellulose, which is quite dirty process and also expensive process. And in this way, the toilet users have paid for the delignification, and you can just produce the nanocellulose right away of the recovered cellulose. And if you then mix it together with the EPS from the activated sludge, and you make a material from the nanocellulose and that the extracellular polymers from, in this case, the granular sludge, you get a material which looks very much like mother-of-pearl material, but has quite high stiffness, and it has very good material properties. Besides that, it also has a nice look. If you mix it just with cellulose, just the raw fibers you get out of the wastewater, also then you can make a nice composite material on the top left side. And that is a composite material of cellulose and microbial EPS, which you can 3D print, which you can mold into all kinds of structures. And we're trying to develop that together with a composite company under the name Replex. You see the term re is quite well liked in commercial terms. Another product we're looking at is producing PHA from wastewater. Now, if you look, PHA, polyhydroxyalkanoate, is a compound which, if you have it, it's almost the same as polyethylene and polypropylene. You can more or less make the same materials from that as what you make from polyethylene and polypropylene. And here you can see, this is a bit to show the commercial value. If you have 3 kilograms of organic carbon and you convert it into biogas, In the Netherlands and US, you will get maybe 10 to 20 cents on the market. And in the Netherlands, you get 60 cents because the government wants you to produce biogas and puts a lot of subsidy on it. But for how long they do that, that's a bit uncertain. If you convert that 3 kilograms of CO2 in bioplastics, you make 1 kilogram of bioplastics. That has a market value of roughly €5 per kilogram. So in economic perspective, much more valuable, but we still have to develop that technology. And the stage of the technology is at a demonstration plant in the Netherlands, at the sludge handling facility. And this plant can produce roughly 50 kilograms of bioplastic per day. So it's a nice plant to produce test material for the material industry. The last one is the extracellular polymers from granular sludge. Extracellular polymers have long not been studied from wastewater, but we started to study that. You can extract them pretty much in the way you can extract alginate from seaweed. The interesting part is you can produce per person roughly 10 kilograms of this polymer per year from the wastewater. And if you mix that with cellulose, you make around 40 kilograms of material per year, which is a plastic-like material. Now we consume roughly 30 kilograms of plastic per year, average on Earth. So you can see that based on the wastewater, we might already be able to produce all the plastics which are now made out of oil. And then we have the municipal waste, if needed, as extra source for all these polymers. So it is an interesting application, and we're looking to all kinds of applications, partly this composite material, partly it's non-flammable, so we look to application non-flammability. Currently, the first applications is in agriculture for all kinds of reasons, but mainly for binder in coatings and pelletization in agriculture, and partly because it has root forming stimulation, so the germination of seed goes better. And on the right-hand side, you see that we can make this material together mixed with clay instead of cellulose. We can make a material which is called nacre, which is almost the same material, which has the same material properties as the shells of crabs and shrimps. And that material has been long sought by material engineers, and they could only do this by layer deposition techniques. We can make this by just general big reactor techniques in a cheap and simple way. And that has also interesting material properties. So to finalize, we are looking to now integrate this fully, that we can extract the polymers, we can also recover the phosphate as needed, but the polymer extraction is done at pH 9 to 10, which means that the remaining sludge after the polymer extraction, all that remaining organic carbon is at pH 9 or 10. If we do the digestion there, then all the carbonate stays in the liquid and the gas will contain only methane gas. It is possible to do the pH, to do the sludge digestion at that pH, and then directly produce green gas and maybe even sequester the CO2, but that's a much longer way to go. And in this way, we then integrate the biogas production. So as take-home messages, pay attention to energy minimization, and we should understand better how this N2O emission is if we want to take it serious, that we want to minimize climate footprint of our installations. In my view, biogas as energy source is a bit overvalued. It is useful. I don't say you should not do it, but be aware and think of using effluent heat integrated better with the city or the villages where you have the treatment plant. And resource recovery is, in my view, a much better way to go in the end than energy neutrality.